Regression Appendix. Economists use a regression to estimate economic relationships such as demand curves and supply curves. A regression analysis allows us to answer three questions. 1. How can we best fit an economic relationship to actual data? 2. How confident are we in our results? 3. How can we determine the effect of a change in one variable on another if many other variables are changing at the same time? Estimating economic relations. We use a demand curve example to illustrate how regressions can answer these questions. The points in figure capital B1 show 8 years of data on Nancy's annual purchases of candy bars, Q, and the prices, P, she paid, superscript 1, which reads, we use a lowercase q for the quantity demanded for an individual instead of the uppercase capital Q that we use for a market. Notice that we violated the rule economists usually follow of putting quantity on the horizontal axis and price on the vertical axis. We are now looking at this relationship as statisticians who put the independent or explanatory variable price on the horizontal axis and the dependent variable quantity on the vertical axis. For example, in the year when candy bars cost 20 cents, Nancy bought Q2 candy bars. Because we assume that Nancy's tastes and income did not change during this period, we write her demand for candy bars as a function of the price of candy bars and unobservable random effects. We believe that her demand curve is linear and want to estimate the demand function. Q equals A plus B P plus E, where A and B are the coefficients we want to determine, and E is an error term. This error term captures random effects that are not otherwise reflected in our function. For instance, in one year, Nancy took an economics course that raised her anxiety level, causing her to eat more candy bars than usual, resulting in a relatively large positive error term for that year. The data points in the figure exhibit a generally downward sloping relationship between quantity and price, but the points do not lie strictly on a line because of the error terms. There are many possible ways in which we could draw a line through these data points. The way we fit the line in the figure is to use the standard criterion that our estimates minimize the sum of squared residuals, where a residual E equals Q minus Q hat is the difference between an actual quantity Q and the fitted or predicted quantity on the estimated line Q hat. That is, we chose estimated coefficients A hat and B hat so that the estimated quantities from the regression line, Q hat equals A hat plus B hat P, make the sum of the squared residuals E superscript 2 sub 1 plus E superscript 2 sub 2 plus ellipsis plus E superscript 2 sub 8 as small as possible. By summing the square of the residuals instead of the residuals themselves, we treat the effects of a positive or negative error symmetrically and give greater weight to large errors than to small ones. Superscript 2, which reads, using calculus, we can derive the A hat and B hat that minimize the sum of squared residuals. The estimate of the slope coefficient is a weighted average of the observed quantities. B hat equals capital sigma sub I, W sub I, Q sub I, where W sub I equals open parentheses P sub I minus P bar close parentheses over capital sigma sub I open parentheses P sub I minus P bar close parentheses to the second power. P bar is the average of the observed prices, and capital sigma sub I indicates the sum over each observation I. The estimate of the intercept A hat is the average of the observed quantities. In the figure, the regression line is Q hat equals 99.4 minus 0.49 P, where A hat equals 99.4 is the intercept of the estimated line, and B hat equals negative 0.49 is the slope of the line. Confidence in our estimates. Because the data reflect random errors, so do the estimated coefficients. Our estimate of Nancy's demand curve depends on the sample of data we use. If we were to use data from a different set of years, our estimates A hat and B hat of the true coefficients A and B would differ. If we had many estimates of the true parameter based on many samples, the estimates would be distributed around the true coefficient. These estimates are unbiased in the sense that the average of the estimates would equal the true coefficients. Computer programs that calculate regression lines report a standard error for each coefficient, which is an estimate of the dispersion of the estimated coefficients around the true coefficient. In our example, a computer program reports Q hat equals 99.4 minus 0.49 P, 3.99 in parentheses, and then also in parentheses 0.08. where below each estimated coefficient is its estimated standard error between parentheses. The smaller the estimated standard error, the more precise the estimate, and the more likely it is to be close to the true value. As a rough rule of thumb, there is a 95% probability that the interval that is within two standard errors of the estimated coefficient contains the true coefficient. Superscript 3, which reads, the confidence interval is the coefficient plus or minus 1.96 times its standard error for large samples, at least hundreds of observations, in which the coefficients are normally distributed. For smaller samples, the confidence interval tends to be larger. Using this rule, the confidence interval for the slope coefficient b hat ranges from negative 0.49 minus open parentheses 2 times 0.08 close parentheses equals negative 0.5 to negative 0.49 plus open parentheses 2 times 0.8 close parentheses equals negative 0.33. If 0 were to lie within the confidence interval for b hat, we would conclude that we cannot reject the hypothesis that the price has no effect on the quantity demanded. In our case, however, the entire confidence interval contains negative values, so we are reasonably sure that the higher the price, the less Nancy demands. Multiple regression. We can also estimate relationships involving more than one explanatory variable using a multiple regression. For example, Moschini and Minke, 1992, estimate of pork demand function, equation 2.2, in which the quantity demanded is a function of income, capital Y, and the prices of pork, P, beef, P sub B, and chicken, P sub C. Capital Q equals 171 minus 20P plus 20P sub B plus 3P sub C plus 2Y. The multiple regression is able to separate the effects of the various explanatory variables. The coefficient 20 on the P variable indicates that an increase in the price of pork by £1, $1 per kilogram, lowers the quantity demanded by 20 million kilograms per year, holding the effects of the other prices and income constant.